Hello, so this is going to be the first episode or video of my CALC 3 playlist. I'm going to try and upload every single day, but I will have a busy summer after these first couple of weeks. I have surf, and I'm also taking DiffyQ over the summer when that starts, but for now I'm going to be doing daily uploads. I'm going to be assuming that you guys, whoever's watching this video, knows how to find unit vectors, how to perform cross products, dot products, and they know how to do addition, subtraction, and scalar multiplication for vectors, because that's typically like the very, very first lesson. It's just a review of vectors. So the very first question we want to answer with this lecture is, how can we draw a 1D line in 2D space, which I'm sure you guys know how to do, and then how would you do the same thing in 3D space? So obviously, you know how to take a line in 2D space. There's two ways we could go about doing this. Of course, you have your XY plane, and then you got 2 points, point 1, point 2. And now say this guy is like point 1 is like A comma B, and then 2 is B comma C. You just find the slope, which is just M equals B minus C over A minus B, and then you plug them into y equals mx plus b. So then y equals mx plus b, plop that guy in there, and then take one of your xy points, put them there, solve for b, and that's one way. Now, if you do the same kind of thing in 3D, however, so you got your xy plane, xyz plane, so this is z, this is y, this is x, and you got the same kind of situation. And say you want to find the line that goes through these 2 points in the xyz plane, so like something like that, and you want it to be 1D, remember. So you're going to take the same sequence of operations. What you're going to find, though, is that this is going to give you a plane. So, I don't know, look something like that. And that plane is going to be going through all of the real z values. So again, you're going to have something that's in this form, y equals mx plus b. Now notice that there's no z in this equation. So this equation isn't dependent on z. So no matter what z is, you're always going to have this y equals mx plus b thing. I think I would compare this to, so yeah, no value of z is going to have an effect on the values of x and y, and vice versa. No value of x and y is going to affect the outcome of z. I guess the way that I like to think about it is kind of like how if you have y equals 1, right? So y equals 1, we'll say that's here. It's y equals 1. Here, you could say like, oh, what is the value? You could ask, what's the value of x for a given y for the graph of y equals 1? It's kind of a weird question because this plot isn't dependent on the value of x. So x is literally all real numbers, and no matter what value of x you are, y is just going to be 1. I guess kind of the equivalent of saying, oh, y equals 1 is the plot right here, is like saying y equals mx plus b in this plane, or in this in these 3 axes, is only this line rather than this whole plane. Similarly, if you took y equals 1 and you put it in 3D space, it's going to be a 2D plane that doesn't depend on x or y, so it's going to look something like that. Okay? So then, to get a 1D line in 3D space, what you could do is you could parameterize it. I guess you basically, in 2D, what this looks like is like this. So we'll take our 2 points again, 1 and 2. Here, let me redraw 2, give them some different, let's do something like that. That's 2 now. So you could interpret these as vectors. So that's vector 1, that's vector 2, right? V1, V2. And if you, like I said, I'm assuming you know basic vector calculations, you could find a displacement vector. You could do either, we'll call it VD, okay, and that's going to be equal to V1 minus V2. You could also say VD is equal to V2 minus V1. The difference is just they're going to be anti-parallel to each other, meaning one of them is going to be going like this, the other one is going to be going like this. It doesn't matter what you do because they're really the same direction. It's just the way you scale them is going to be opposite. So I guess for here, we'll just say it's V1 minus V2. So out of here, we're going to get this VD, right? And this VD is going to be, it's a displacement vector, so he's going to be starting at one point. I guess V1 minus V2 would be going this way, right? So that's VD. And notice he's like on, if we wanted to just eyeball a line, it would kind of look like this. And VD lies on that line. So if we wanted to plot out this whole line, we would just do T times VD. So you're just multiplying this vector by a scalar, and you know, if you do any like real value of T, you're just gonna have a really long vector that lies on that line, and you get the line. But here's another problem. We interpret, this is like what the slope of that vector looks like, but realistically, all vectors, if you're not adding them to something else, are going to be anchored and pinned at the origin. So what we have right now with T times VD is really just this. And then this is like VD that we found earlier. And you're just scaling him by T. So I guess all we have to do is take either this point or this point and add them to that guy. So we could anchor them, rather than them being at the origin, they're anchored at either, like at one of the two relevant points. So we'll call that like R naught, okay? And that could be, again, either this or that. And that's going to be your expression for R of T, okay? And it does look pretty similar to like y equals mx plus b. I guess it's like, I guess it would be xm plus b equals y. You could kind of see like this is analogous, or this is analogous to that kind of thing. This is analogous to this. You know, you get the idea. So yeah, this is useful in 3D space because it keeps to get a 1D line, because all you're doing is you're getting a vector, a displacement vector that's already 1D. You're scaling him. That's going to maintain its dimensionality. It's still going to be 1D. And then you're adding him to another 1D vector, so he's still going to be one-dimensional. And that way you're not going to get this plane up here. Okay, so yeah, and in 3D this is going to be the same kind of thing, where if you have XYZ plane, or whatever you want to call it, X, Y, you have point here, I don't know, point here. We'll say this guy's like up there, this guy's up there. You interpret them as vectors. You subtract them, you're going to get, I don't know, this. And then scale him by T. He's going to be mapping, well, remember he's at the origin, so he's going to be mapping this. And then you add him to one of the two anchor points, and you're going to get that line you want to trace out. So if you have, take point 1 to be 1, 2, 3, and then point 2 to be 5, 2, 3. You could kind of draw this. And obviously, by doing this kind of approach, you're not limited to just like, oh, I'm stuck in the XY plane and I have to do this slope calculation up here. It's just the same kind of approach. So 1, 2, 3 is going to be like, I don't know, something like that. and then 5, 2, 3 is going to be something like that. We're going to, well, he's going to be in the same, it'll appear just more forward, just to give him some dimension. That's how we're going to draw him. And then you interpret these as vectors. So you're going to do either P1 minus P2 or P2 minus P1, and you're going to get a vector that's generally in this direction. So for our displacement vector, we'll do P2 minus P1. We're going to get 4, 0, 0. And then you'd multiply this guy by t. And then you add him to either P1 or P2. We'll just do P1. And then that's going to be your R of t. And then I guess some important observations about this is that when t is 0, you're going to be found at your anchor point. So you're going to be found right here when at t equals 0. And if we said that this guy, instead of being P1, if this was P2, so if this guy was 5, 2, 3, then same thing, t is 0, you're going to be starting at 5, 2, 3. And then scaling it is going to be different. So if this is our VD, and then we're multiplying him by t, and we did P2 minus P1 in this scenario, and we multiplied him by negative t, he's going to flip directions. And then he could scale by negative t in this direction. But if our VD was oriented the other way, so that's our new VD, and we did P1 minus P2 in this scenario, and we multiplied him by negative t, he would be pointing in the other direction. But the important part is they span out, or that, well, they would be pointing in the same direction. It's just the values of scaling are going to be different. So yeah, so then you're probably wondering then, how are we going to be drawing 2D planes? How do we manipulate the planes and give them more dimension instead of just being straight up in the Z like that? So you could use, so imagine you have like a plane. So you have X, Y, and Z, X, Y, and Z, and then you have some kind of plane that goes like this. Okay. You could take the vector that's normal, meaning like orthogonal to any point in this plane. So this guy is like N, and he's any kind of vector that you draw in this plane. So like this guy, he's going to be orthogonal to that guy. Okay, so I don't know, call this guy X. Then that means we know that N dot X is 0, right? Because two orthogonal vectors dot product are going to be 0. We could use this to illustrate like an equation for a plane for whatever points we want. So what we're going to say is, again, let's take another plane. And we have our normal vector right here. So this guy's elements of A, B, and C. And then we take a known, let's take this guy right here. He's just a plane in the, or a point in the plane. He's X naught, Y naught, and Z naught. And then we take any arbitrary X, Y, Z point that's also in the plane somewhere. We're not quite sure what its values are, but he's arbitrary. This guy is going to be X, Y, Z. Then we could dot product. And so this vector between them is going to be X minus X naught, Y minus Y naught, and Z minus Z naught. Okay, and we know that N dot this guy, we'll call the vector as a whole V, is 0, and then we could simplify that to A, B, C dot X minus X naught, Y minus Y naught, Z minus Z naught, that equals 0. Simplifying this more, you're going to get A x minus ax naught plus by minus by naught plus cz minus cz naught equals 0. And then finally, you'll get ax plus by plus cz equals ax naught plus by naught plus cz naught. And this is the equation for a just an arbitrary plane. But typically, we use this one. We just do ax minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. So this is just x. This is a point that you know, y, point that you know, z, and a point that you know, just points that are given to you. And then a, b, and c are just the elements of the normal vector for that plane. And then you just solve this out, you get it into this form, and that's going to be like your equation for a given plane. So if we had a plane, for instance, 2x plus 3y plus z equals 0, its normal vector is just going to be 2, 3, and 0. And yeah, and in order to draw a plane, you're going to need 3 points. Before, to draw a 1D line, we needed 2 points, but now we're going to need 3 points in order to give it some dimensionality, right? If you had 2 points only, then there's a lot of ways you could draw a plane, because you have this line between them, and then the plane could go like this. It could be coming right at you, like that. It could do anything, but we need a 3rd point in order to give it. Say if we had this point, then we know that the only plane that goes through all 3 of these points is this plane right here, rather than this other first plane that I drew. And then, so if we had those 3 points, you do a vector thing again, where you do one of these vectors, these displacement vectors again. So if this is v3, this is v2, this is v1. You just find these displacement vectors, and then you would cross product them. You would take their cross product, because we know that a cross product is going to yield a vector that's orthogonal to both of them. And then once we do that cross product, this is going to be our n vector. And then you would do this entire procedure up here. We have this times, or I guess this right here, a times x minus the points of one of these 3 points, and you have to keep it consistent. So say you have the v3 is just, or this point p3 would just be 2, 3, 8. Then you would have to keep these consistent. So it would just be a times x minus 2 plus b times y minus 3 plus c times z minus 8. And then depending on what numbers for a, b, c you get out of the cross product you do, those are going to be plugged in. We already plugged in our x naught, y naught, z naught, and then you just solve, and you're going to get something in this form. And then that's your equation for that plane. So you have these lines, you have these planes, and you could form interactions between them. So if you have, I guess we could start with lines. We know that if you're in 2D space, and you have, I don't know, one line that's here, and then one line that's like here, these are most definitely not parallel, right? If I kept drawing this guy, it's going to go somewhere here. This guy's going to intersect. So we know that in 2D, if 2 lines do not have the same slope, they're going to have to intersect at some point. But in 3D space, that's not necessarily true. They can intersect at a point, but just because they don't share a slope doesn't mean they will. When these lines don't intersect, they're called skew. So you're gonna be drawing 2 lines in 3D space with the parametrization method we took. So say these form a line that you illustrated where you have this and that. And you get your VD, you multiply it by t, move it to one of these guys, plus R naught, we'll call them R naught 1. And then you take another 2 points right here, same exact procedure. These guys does not mean that they're going to intersect, and they're going to be called skew. Now for planes have some more interactions. If you have, so for two planes to be parallel, so what that's going to look like is like that kind of. Let's see, you have one plane up here, and then you have another plane up here. You could tell that these are parallel. They're not really going to intersect. What that really means is that they're normal vectors. Doesn't really matter how you draw their normal vectors. You could draw them this way or that way. Doesn't really matter. The point is that these two normal vectors, n1, this will be n1, this will be n2. n1 is going to be some constant times n2. In this scenario, these planes are going to be parallel, and they're never going to intersect, because two vectors that are pointing in the same direction but are scalar multiples of each other are still parallel. So if you make this observation that a1x plus b1 plus, or b1y plus c1z equals 0, and then you have another one, a2x plus b2y plus c2z equals 0, and you have a1, b1, c1, so you have a1, b1, c1 equals some constant times a2, b2, c2, then those two planes are parallel. And then these two planes, they'll be orthogonal. You could kind of sense a pattern here. Planes are parallel if their normal vectors are parallel. So if for two planes to be orthogonal, this is going to be kind of annoying to draw. So for two planes to be orthogonal, their normal vectors also have to be orthogonal. So this will be n1, and then this will be n2. So n1 dot n2 is going to be 0 for those two planes to be orthogonal. So also notice that when these two planes intersect, they're going to form this line of intersection, which you can parameterize. How you can parameterize this is, so say in this case, you know they're orthogonal, so you could kind of geometrically see that their cross product is going to produce a vector that points in the direction of that line of intersection. And so you just do t times n1 cross n2, and that's going to give you the thing that you, the vector that you're going to be scaling. As for a point, remember this vector is going to be at the origin. He's pointing in the right direction, but he's at the origin. So to get him to be at an actual relevant point, you need to choose a point on this line that they share. Typically, that's not something you really need to worry about. If you do this much, you could see it in the answer choices, which one checks out. You could also test the points that they provide in the answer choices to see if which one actually is shared by both of the planes. So now we're going to move on to those. I just gave a quick rundown of what's going to be happening. This is kind of more of a review lecture thing. So now we're going to be doing 3 past exam questions. So this first one is from the final of spring 2025. So it's just telling you, find the equation of the plane containing the points 1, 1, 1, 1, 2, 3, and 3, 1, 0. So this goes back to finding, to the equation of finding a plane. You need 3 points. You cannot do this with 2 points. So this isn't really, it's not really that important to draw something really like descriptive with a lot of detail. How I approach these problems is I just do a triangle, and it really doesn't matter how you draw it. You don't even have to consider drawing them out on a plane. So I'm just gonna call these points. Okay, I can't even. All right. So let's just say we find this vector, and then this vector. So let's do v1 and then v2. I'm not really concerned about direction either, so I can do this point minus that, or this point minus that. Doesn't really matter. But for v1, we're gonna have 1, 2, 3 minus 1, 1, 1. That's gonna give you 1 minus 1 is 0, 2 minus 1 is 1, 3 minus 1 is 2. And then for v2, we're going to do 3, 1, 0 minus 1, 1, 1. And you're going to get 2, 0, minus 1. Okay, so these are these vectors, but remember, to find a plane, the equation of a plane, we need a normal vector. So we have 2 vectors that are pointing in the direction of a plane, right? So these vectors, if you scaled them up by some value, they're going to trace out a plane. But we want a vector that's normal to that plane. So we could take a cross product, and it's going to give us a vector that's orthogonal to both of these vectors, and we could use that to find the equation of the plane. So we have, so to take a cross product, you just do I, J, K, then we'll do V1 cross V2 or V2 cross V1, does not matter. We'll just do V1 cross V2. So for V1, we have 0, 1, 2. For V2, we have 2, 0, minus 1. And you're going to get, let's see, so if you do cross this out, you're going to get 1 times negative 1, that's negative 1, minus 0, so it's just negative 1. For the second element, you're going to get 0 minus 4, which is minus 4, but the middle entry of a cross product is a negative, is always opposite what you would get, so this is just going to become plus. And then for k, 0 times negative 1 is 0, minus 4, minus positive 4, or, yeah. So you have that. So your normal vectors, just for clarity, negative 1, 4, minus 4. And then remember, we just plug this into the equation. So this is A, this is B, this is C. So you have A, which is negative 1, times x minus one of the given points they gave us. I think I'll choose 3, 1, 0 because that has a 0 in it, and that just makes our job a bit easier. So for x naught, we have 3 plus b, which is 4, times y minus 1. And then minus c times z minus z naught, which is just 0. And then this equals 0. So if you simplify this, you get negative x plus 3 plus 4y minus 4 minus 4z equals 0. And then if you simplify this a bit more, you get negative x plus 4y minus 4z. This video made a silly mistake with the cross product. This entry, the last entry, this guy, should be 0 times 0 minus 2. So this guy is minus 2. So our new normal vector is going to be minus 1, 4, minus 2. Okay, so we're going to do the same sequence. We're going to end up with negative x plus 4y minus 2z equals 1. And if we look at option B up here, if we multiply our result by negative 1, you would get exactly what option B says. So, yeah, so our answer is option B. Scalar multiples of each other are okay to deal with in this, in these kinds of problems. So now there's 2 more problems. This one wants us to find the equation of a plane that contains this point and is also perpendicular to these other two planes. So you can kind of imagine two planes. I don't know, they're in some kind of orientation. They don't necessarily have to be, here, how can we, let's do this. They don't have to necessarily be perpendicular to each other, but in order to get something that's perpendicular to them, you have to get, you just really observe their normal vectors. So if you, so this is n1, this is n2. If you take the cross product of these guys, you're going to get something that points, remember, along their line of intersection. And then when you, now we're given, so we have this line of intersection, and now we're given a point to match it on. So say this is the point you want to match it to, then you'd just be extending it out to that point, and this plane would be orthogonal to those other two planes because its normal vector, the normal vector of this new plane, is orthogonal to the normal vectors of the other two planes. So you would just harvest whatever normal vectors you get from these equations. So for the first one, you have 2, 1, minus 2. And then for the second one, you have 1, nothing in the y spot, so that's just 0, and then 3. Now you take their cross product, and you're going to get 3 minus 0, that's just 3. And now for the middle, you're going to get 6 minus negative 2, which is 8, but you take the negative of the whole result. Wait, what did I say? So you have negative 6 minus negative 2. This is just negative 8. Yeah, so you have negative 8. And then now for the last one, you just do 0 minus 1. So it's just minus 1. So this is the normal vector of this new plane. So it's this guy. And now they give you a point that you know is on the plane. So you just do the same operation as before. You do a times x minus x naught plus b times y minus y naught plus z times c times z minus z naught, and you solve it. So you have 3 times x minus 2, the point they give you, minus 8 times y minus 1, minus 1 times z minus 1 equals 0. You get 3x minus 6 minus 8y minus, or plus 8 minus z plus 1 equals 0. And then you could simplify this to 3x minus 8y minus z, and then if you add 8 and 1, you get 9. 9 minus 6 is 3 on this side. Subtract 3 to both sides. It's negative 3, and that's option E, which is exactly right. Now for this last one, this deals with line parametrization. Line parametrization and it's like the line of intersection we were talking about. So it's a little bit less lengthier than this. So again, it gives you two planes. So you could picture two planes. You don't really care about how they're oriented. And it's, I don't know, something like that. And you care about this line. So you just take their normal vectors, right? And then you take their cross product. You're going to get a vector that's pointing. You could kind of almost see that this is orthogonal to these, and it's also pointing in this direction. So let's see, you take the cross product of n1 and n2. So this one, so if this is our n1, you're going to have 1, 2, 3. Because remember, the elements a, b, c are just the coefficients of x, y, and z in the plane equation. And then n2, this is negative 2x. I wrote that down wrong. Yeah, so this is going to be minus 2, minus 1, then plus 1. So you take their cross product, you're going to end up getting 2 minus -3, so that's just 5. And then this middle one is going to be -1. Well, it's going to be 1 minus -6, which is just 7, but it's the middle component, so you do -7. And then for the very last one, you're going to get -1 minus -4. So you're going to get -1 plus 4, which is 3. And that's perfect because that lines up exactly with option F, which, yeah, it is the right answer. And you did see, for this, you don't even have to look at what points this shares. You just see that this vector is the same. And if option F was, for example, 10 minus 14, 6, this is parallel to the result that we got. It's just it's just because if this is vector 1 and then this is the vector that was in the answer choice, this would still be right. Well, actually, yeah, this would still be right. You just have to, because you know that they're parallel, because v1 equals k times v2. In this case, k is 2. So this would still be right if these numbers didn't line up. So be wary of that. So yeah, that concludes first video. I hope I taught okay. I'm not quite sure. Just give me suggestions and I'll try and keep improving. Thank you.